Okay, we're going to go ahead and start chapter 6.1. So we're talking about operations on functions. So what are we talking about? Remember, we can have a function, maybe we'll call it f of x, and maybe that function is 3x minus 2. Okay? And remember, we're just really talking about this expression, okay? And we're giving that expression has a name, okay? So if we had a second function, g of x, maybe this one is like, I don't know, minus x squared plus 2x, then we can start to do operations with functions, plural. So it's very simple. If you want to add functions, say I want to do f of x plus g of x, guess what? I'm just going to make those substitutions. F of x is 3x minus 2, and I'm going to add to that g of x, which is negative x squared plus 2x. And then it's a simple matter of simplifying, making sure everything's in a nice standard form. A standard form would be in decreasing order of the exponent, so let's do the x squared first, plus 5x minus 2. So very simple to add. You could do the exact same thing and subtract two functions. Just remember, subtraction is going to need to have, distributive power there. So we're going to have the first function, 3x minus 2, minus the second function. You start to see why I used a parentheses, okay, because what's inside the parentheses is representing g of x. And I have to subtract all of it. So 3x minus 2 plus x squared minus 2x, and then I'll go ahead and combine my like terms with an x squared plus x minus 2. So adding and subtracting functions is the same exact thing as adding and subtracting expressions. Okay, we just want to give them names. Okay, let's try two different functions now. So now we have this new f and this new g, and I have defined each function. And we're just going to continue in the same vein, operations, because you can do f times g, okay? And I could have written f of x times g of x, but I've decided to be a little bit lazy and I dropped it, okay? It's just f times g, because then I can say that's one thing and that's going to be a function of x. So those are both saying the same thing. I can use either notation. And it just means the same thing. Maybe here it's a little more obvious. I would take f of x, which is x plus 1. I love using parentheses, times the g of x, which was 2x minus 3. So make sure you're using your good FOIL practice, 2x squared. Plus 2x minus 3x gives me minus x, and then the minus 3. So that would be my answer for multiplication. And then, of course, we can do division. Same idea, nothing's new here, guys. And we're going to have only a little difference in domain and range then. So f of x was x plus 1, and I'll divide by 2x minus 3, and that would be the simplest form right there. Okay, here's a really good time to talk more about domain and range, okay? When we were talking about linear or quadratic, we always said, let me give an example, 3x plus 1, maybe x squared minus 3. And we always said the domain was all real numbers, okay? And in the case of linear, the range would also be all real numbers. But for quadratics, we had to find the vertex, right? And figure out that maximum or minimum y value, okay? So it was a bit of work. So I want to go back to domain, though, and when we're talking about something that's not linear or quadratic. In the last example, I can't remember exactly what it was, but let's make another one up. Let's say I had a new f over g, and it was something like x plus 1 over 2x, let me back that up. Let's just call it x minus 5. Okay, so remember, find the domain is the question. And when I look at the numerator by itself, x can be anything at all. When I look at the denominator, x can be anything at all. But the problem comes because I've put them together so that the x minus 5 is a denominator. And the thing is, you are not allowed to divide by 0. Okay? So you want to make sure when you're telling a domain that you never divide by 0. Okay? So if you want to put it in a rule, I would say denoms do not equal 0. So what happens in this problem is you look at where's my denominator. Well, so I'll make a substitution for denom in this equation, and I'll say x minus 5 cannot equal 0. Ooh, guess what? That leads to the statement that x cannot equal 5. So you have this domain where we thought it was all real numbers, and it still is all real numbers, except, you got to remember, x cannot equal 5. So that becomes your domain. All real numbers except for that x cannot equal 5. Okay? Alright, so I want you to go ahead and try this one. I want you to find the domain when we have a function that's x plus 3 over 2x minus 5. Go ahead. Alright, I'm coming up with the domain is all real numbers except that x cannot equal 5 halves. Because remember, I had to remember the rule that denominators do not equal 0. So 2x minus 5 does not equal 0. So 2x does not equal 5, and x does not equal 5 halves. Okay? So that's finding domain when you have a quotient. Okay, so we want to talk about something that's called composition of functions. Composition is this very special word, okay? And let me show you the symbol we use for it. If I have a function f and I have a function g and I want to take the composition, I do f open circle, so it's exaggerated, it's not an O, it's an open circle, f composite g. Okay, so that's f composite g of x. I could have written this as f of x composite g of x. Okay, so this open circle is a special symbol that means take a composite. Now what does it mean to do though? Kind of the definition of this, okay, is it means take the function of the result of g of x. Okay, so that's what kind of be a working definition for us for a composition, and let me kind of show you a little bit what that means by using these two functions I've shown up above. Say for example, I want to do f of g of 7. Okay, so what I have to do first is you always do the inside first. Okay, so first thing I have to do is find what is g of 7. So leave the f parentheses alone for the outside and just work on this inside part. What is g of 7? Well, this up here, okay, is going to define what g of is. So here's 7 for x, and it gives me a y value 0. So this tells me that g of 7 is equal to 0. That's what that tells me. So I can make a substitution, g of 7 is 0. Okay, so I'm left to find the f of 0. So I found the result of the inside function, g, and now I'm going to use that as the input for the f function. What is f of 0? I'm going to go back up here, okay, so f of 0 is equal to a negative 1. So that becomes a negative 1, and that's my answer to the composite. Okay, this was a f composite g of 7. That's just another way to write this. I feel like we better try another one of these, so let's try this one more time. Let's do f of g of 4. Okay, let's try 4. And what we're going to do is we're going to first find out what g of 4 is, because that's on the inside. You always have to do the inside first. So go back up to your g function and find what g of 4 is. G of 4, okay, remember, this 4 is taking the place of x in g of x. So when x is 4, the y value is 9. So g of 4 is equal to 9. This g of 4 can be replaced with 9. So f of 9. And then it's a matter of finding what is f of 9. So go back to the f function. When x is 9, what is the y value? The y value is 4. So that's equals 4. And that will be my answer. Okay? So this is taking a composite, and it's all about the input. You got input to G, get an output of G, and that becomes the input to F. And then you'll get the output of F, okay? So it's important that the kind of output of G has a place to go in F, okay? So could you find an example where that doesn't work? Let me look at this for a minute. So what output of G, the 0 or the 7, the 9 or the 2, has nowhere to go? Well, guess what? They all have a place to go. So everything would work here. We could do all the F composite G's. So here's a new one, F and a G. Let's see if you could find F of G of, pick a number, let's try 8, okay? That's just another way of writing F composite G of 8. Okay, so these two things are identical. And I want you to go ahead and figure those out. So pause it and I'll show you how to do it next. Okay, so if I'm going to do this, I'm going to just go ahead and do it out. This becomes F of the G of 8. I need to figure out what G of 8 is. G of 8 is right here. Here's the 8 going in, and here's the 15 coming out. So now I can replace G of 8 with 15. Now I have to figure out F of 15. So I go up to the F. Here's the 15 going in, and here's the 11 coming out. So I get 11, and that's my answer. Alright, I want to point out one other thing. If you were trying to take an F composite G of 10, you would call that F composite G of 10. So you start with that working definition where you use the 2 parentheses instead of the composite symbol. But then we're going to do the G of 10, do the inside first. So I'm going to replace G of 10 right here. There's the into G and then 14 coming out of G. So F of 14. But then what you do is you look at this and you say, okay, so I have to find F of 14, but I don't have any 14s for X. So I don't know what to do with that. This is not possible. Okay? And you're kind of stuck. Okay? Okay, we certainly want to be able to do F of X and G of X algebraically. So we have these expressions again instead of just a set of points. So let's imagine I'm taking F of X, composite G of X, and you'll notice I'm almost using a different way of writing this every time, so you can get used to all the different ways. But as long as you see this composite symbol, you know what's going on. So I'm going to write it. I always start this way by writing it as the 2 parentheses, this working definition. So F of G of X, and then close your parentheses. And then I always work from the inside out. So the next thing I'm going to do is find a substitution for G of X. So I'll leave, let me keep my colors, I'll leave the F of alone, but the inside has to be replaced with G of X. But here's what G of X is right there, X minus 6. So I make that substitution. Okay? Now I'm going to figure out what is F of X minus 6. So remember, this X minus 6 is the input. It's going to replace this X here in the definition. Alright? So instead of having it just an X, like I had up here, now I have an X minus 6. So let me go up here and redo this where I replace that X with my X minus 6. So that X becomes X minus 6, and remember it got squared, okay? But then I had to do the plus 2, so that gets tacked on here at the end. So that's a composite function, and that's really the hard part of what we'll be doing. And now it's a simple matter of simplifying everything. I'll make sure I FOIL this correctly, and then I'll gather up my like terms, and I'll call it done, because that's in a nice standard form. Okay, so I've written the same two functions again this time. These are the same ones we just did, f composite g, because I want to point out something. We can actually do this in any order. We could do g composite f. And just remember to keep things in order. The g came first, so g of f of x, making sure we're using those two parentheses so we have an inside, and then we'll do the outside. This time, the inside is f of x. So let's keep the g on the outside, and let's go make a substitution for f of x right here. F of x replaced with its expression, x squared plus 6. Cool. Now I have to evaluate the g. So evaluating g says take your input, okay, write it down, and then subtract 6. So I'm going to take my input, x squared plus 6, I'm writing it down, and then I have to subtract 6, and so I'm getting a simple x squared as my answer for g composite f. Okay, so it can go both ways. So what I want you to do next is a couple of examples. Okay, I want you to do these 3 questions for me. One is just to find f of x minus g of x. The second, find the quotient, and also give me the domain of your quotient function. And then I also want you to take the composite. I want you to get those answers, and I want you to email them to me. Cool? All right, see you in class.